Hi, this is the video for section 3.1 of a student's guide to the Schrödinger equation. This one's about the origin of that equation. Notice I try to be careful not to use the word derive unless I put it in quotes, because as Richard Feynman said, it is not possible to derive this equation. As he put it, it came out of the mind of Schrödinger. What he means by that is it didn't come from first principles. So where did it come from? Well, Louis de Broglie had been working on what he called matter waves. He said, if waves sometimes behave like particles, as in the photoelectric effect, then particles may behave like waves. And Schrödinger realized for things that behave like waves, we should be able to write a wave equation. But of course, the classical wave equation has second-order partial derivatives, both space and time. And the Schrödinger equation is first order in time, and it has one other very beneficial feature, which is that it's complex. That is, that the terms involve the square root of -1. So, to understand one way to at least justify, if not derive, the Schrödinger equation, we're going to use conservation of energy, specifically the classical equation, which says the total energy is the sum of kinetic plus potential. And to get from there to the Schrödinger equation, it really helps to use this relation, often called the Planck-Einstein relation, which relates energy to frequency. In this case, linear frequency. In the case of omega, angular frequency. When the constant of proportionality is either h for linear frequency, that's Planck's constant, or the modified Planck constant h over 2 pi, or h bar, if you're using the angular frequency. That's an equation that describes the energy in waves because omega, or f, frequencies are properties of waves. But in the 1860s, James Clerk Maxwell was working on electromagnetics, and specifically radiation pressure, and he wrote a relation which said that electromagnetic waves carry momentum, and the amount of that momentum is given by their energy divided by their velocity, in this case the speed of light. So if we say these matter waves that de Broglie was hypothesizing behave like other waves, we can write their momentum as E over c, and if we use Planck-Einstein, we can write E as h bar omega. Now that may not look very much like the Schrödinger equation, but it helps to take another step, that is, to relate frequency and wavelength to the speed of light, and omega is 2 pi f, so if we plug in c over lambda for f, we get this expression, and if we cancel out the c's, we find that momentum is equal to h bar times 2 pi over lambda. But 2 pi over lambda is familiar, that's a wave number. So we can write h bar k as the momentum of a matter wave. And this really does begin to get at wave-particle duality, because momentum is something we normally associate with particles, and wave number is something we normally associate with waves. So let's write down the energy. In this case, the kinetic energy, 1/2 mv squared. We know that momentum p is mv, so if we plug that in, we find that kinetic energy is p squared over 2m, or if we use this expression for p, we get kinetic energy is h bar squared k squared over 2m. So for the total energy of a matter wave, we can write the energy is Ke plus V, the potential energy. Notice this is not potential. If you've taken a course in electromagnetics, you probably think of V as the potential energy per unit charge, which we call the electric potential. In quantum mechanics, we tend to use V as the potential energy. So we're going to write that together with the kinetic energy and set that equal to the total energy. But Planck-Einstein tells us that the energy is h bar omega, so we now have this relation, and we're at least beginning to see some of the terms that are present in the Schrödinger equation. But in order to make that next step, we really have to assume something about quantum wave functions. Specifically, to say that one form of a wave would be a plane wave. If you're not familiar with plane waves, it might help to jump forward. Here in section 3.4, on page 82, you'll see drawings of waves that are somewhat indicative of what a plane wave would be. Notice here is the more wave-like structure, something that looks like a sine wave that you're maybe more accustomed to. And notice that the surfaces of constant phase, that is, say, all the peaks. I could have drawn all the valleys, but I chose to do the peaks here. Those surfaces of constant phase are all flat planes. This one's going along the y-axis, this one's going at some angle, but these are all forms of plane waves. So that's what I have in mind when I think of a plane wave. And the mathematical expression for such a wave can be written like this. psi of x and t. That's the function psi that depends on position x and time t, is written as ae to the I kx minus omega t, where a is the amplitude of the wave, and the phase of the wave is given by this expression here. Phase is written as kx minus omega t. And what does the phase tell you? Well, remember what e to the I phi is. E to the I phi can be written using the Euler relation as cosine of phi plus I sine of phi. So what kx minus omega t, that is phi, is telling you is what part of the sinusoidal oscillation you're in at any given location x and at any given time t. And with this expression for a plane wave, and this expression relating omega and k squared and potential energy V, we can get to the Schrödinger equation. How do you do that? We'll start off by taking the partial derivative of the wave function psi with respect to time. Plug in our expression for psi. That looks like this. The only term involving t is this one. So when we take the derivative with respect to t, it's going to pull a negative I omega out front, leaving the rest of it unchanged, but that's just psi again, so we get negative I omega times psi of x of t. Again, that's the first temporal or time derivative. That's cleaned up a little right here, so you can see that relation between the time derivative and omega. Solving that for omega, it looks like this, and here we've pulled the minus I into the numerator, which just becomes I. So that says where we see omega in our energy equation, we can now substitute this. But the Schrödinger equation also has space derivatives. So let's take the first partial derivative with respect to x. This is a term that involves x. That's going to pull an ik out front, leaving the rest unchanged. That's ik psi. Now you're probably thinking we're going to solve for k, but not yet. This is, in fact, the first spatial derivative, and instead of solving for k, we're going to take a second spatial derivative. That means we take the derivative of this first derivative. That pulls another ik down, and the two i's combine to give a minus sign, and the two k's combine to give a k squared, or this expression, which can be solved for k squared, and it gives us minus 1 over psi times the second partial derivative of psi with respect to x. And since our energy equation had a k squared in it, this is going to be useful. So the part of our energy equation involving h bar omega looks like this. I've just pulled the I out to the front here. And the part involving h bar squared k squared over 2m plus v, now we're going to plug this in for k squared, and we get this. So we're going to set this on the left side and this on the right side. And since there's a psi in the denominator of these two terms, we're going to multiply through by psi. That'll cancel that, and it'll give us a v psi, or this expression. And now we're there. This is the most common form of the one-dimensional, time-dependent Schrödinger equation. Later on, we're going to see a time-independent version. That's why this is called the time-dependent version. In the next section, we're going to go through each of these terms and talk about their physical meaning. But remember how we got here. There's a little review of the fact that we wrote the total energy as the sum of kinetic and potential, and then we used the expression for a plane wave and took derivatives to substitute for omega and k squared. And it's been my experience that when people see this for the first time, they say, wait a minute, this expression holds for plane waves, but what about other quantum wave functions? Plane waves go on forever in space and time. They're just not that interesting. They're not physically realizable, for one thing. But as it says here, one good reason for using this equation for more complicated quantum wave functions is that it works. That is, it gives predictions that agree with measurements. But why should it work if we derived it based on only a simple plane wave function? Well, the answer is, this is a linear equation. That means that it has the wonderful characteristic of superposition. Superposition means we can combine these simple plane waves in proper proportions to produce more complicated waves, and those will also be solutions of the equation we just derived. So as it says here, judicious combinations of plane waves lead to a variety of quantum wave functions. We'll talk a lot more about that in Chapter 4 when we deal with Fourier analysis. So how exactly does that superposition work? You'll see some very specific examples in later chapters, but generally, imagine this. A single plane wave, as I said a minute ago, goes on forever in space and time. So if we want to localize it, make it into a wave packet, we've got to combine that plane wave with other plane waves in just the right amount and with just the right phase so that they cancel in some locations and reinforce in others. For example, here's psi of x and t, written as amount A1 of a wave with wave number k1 and angular frequency omega 1, plus a different amount, A2, of a wave with different wave number and angular frequency, and so on. You can combine as many of these as you need to produce the function you want. Reinforces here, A sub n determine the amount of each plane wave. And if you want to do this over a continuous spectrum, that summation becomes an integral, and instead of discrete A sub n's, you have a function of wave number, which we've called A of k here. In this case, A of k is the amplitude per unit wave number. So, just like for individual plane waves, if we take the first order time and space derivatives, we can get to the Schrödinger equation for this packet of waves instead of an individual wave. One thing that's going to be useful later is to pull a factor out of that A. We're going to call it phi of k now because we've changed it by pulling this 1 over the square root of 2 pi out of that A. So this function differs by a constant from A of k. We do that because of the Fourier transform relationship we're going to get into in chapter 4. So we're going to see what each of these terms means, but before we do that, here's another form of the Schrödinger equation that you're very likely to see. It's on the cover of the book for one thing, and it's got the familiar first time derivative on this side, and on this side, instead of the second spatial derivative and potential energy term, there's an operator, an h with a hat on top of it. What does that mean? That's the Hamiltonian, also called the total energy operator. If we look at what that must be, given our Schrödinger equation, it must be equal to this second derivative term with the negative h bar squared over 2m in front of it, plus the potential energy times wave function psi. So we can write the operator itself without the wave function as just h hat. Looks like this. This is the Hamiltonian operator, and this is the Schrödinger equation written using that operator. Why should this total energy operator have terms like this in it? Well, it's just a slightly different flavor of what we've done before, using de Broglie's relation between momentum and wave number, and the Planck-Einstein relation between energy and omega. If we write our plane wave instead of with k and omega, if we use these to solve for k and solve for omega and plug those in, you get a p over h bar and an e over h bar, and that makes the plane wave function look like this. Then, when you take your first spatial derivative, this term comes out, or solving for p psi, it looks like this. So that means we can define a momentum operator, which is going to operate on a wave function, and it must have a negative IH bar times a first spatial derivative. If that's the momentum operator, total energy is kinetic, p squared over 2m plus potential energy, v. So now we're going to put this in for our momentum operator. That means we get this guy squared. And to see how that makes sense, remember, when you have an operator squared, it does not mean that you apply the operator to a function and then square the result. It means you operate on the function and then operate again on the result. So in the case of the momentum operator squared, it is the momentum operator applied to the momentum operator applied to a function. That means you take this derivative of this, and when you do that, it looks like this. So the momentum operator squared is actually this function, and when you plug that in, you get exactly what we earlier defined as the Hamiltonian, or total energy operator. We're going to go through in the next section what each of these terms means, but you should note here that your quantum book may have an alternative approach, or if you're just curious about alternative ways of getting to the Schrödinger equation, there is something called the probability flow approach and a path integral approach that you can find briefly described on the book's website, along with some links to helpful other websites for those approaches. That's it for this section.